I'd like to thank the organizer for giving me a chance to speak here. Today, I'd like to discuss so-called pseudo entropy, which is the generalization of the entanglement entropy. And this generalization is actually inspired from the holography argument or quantum gravity. But today, I will in particular discuss its application to the quantum many-body systems. And main message is this talk is we can find such a generalization, pseudo entropy or something other from the some natural argument in the within the gravity. And as I will tell you later, we can see very nice correspondence between tensor networks and gravity in ADS. So main message is that probably we can do the similar things. I mean, we can learn something new quantum information theoretic quantities from the purely tensor network argument as well as quantum gravity. Okay, and this talk is based on several my work in collaboration with Yoshi Nakata-san and Tadashi Takanagi-san, Yusuke Taki-san, and Jisha Wei-san, and Morabashi, Nobuo Shiba-san, and Kanato Goto-san, and Masahiro Nodaki-san. So, okay, by the way, please interrupt me anytime you want. I can answer question anytime. Okay, and this is a plan. So since I suppose we have broad background, let me first share the basic background of this work and also share the motivation. And then I would like to discuss some heuristic derivation of pseudo entropy, how we come up with such a generalization from the argument of the gravity. And then I move to the more formal part, formal definition of pseudo entropy and its basic properties. And finally, I will discuss application of the pseudo entropy to the quantum many-body system. So today I don't discuss very much about gravity application. If you are interested in that part, please look at our paper. Okay, so first let me start from the interesting connection between entropy and area in quantum gravity. So if we want to keep the second law of thermodynamics, even in the gravitating system, we need to assign the entropy for the space-time or, for example, black hole. And it's known that it becomes known that black hole entropy is proportional to the area of the black hole horizon. It's found by Bekenstein, and later Hawking fixed the overall coefficients. And it sounds interesting or a bit strange because although black hole seems to be a very high energy excited state, its entropy proportional to the area, not the volume. But this, if we take it seriously, actually this gives us the idea of the holographic principle. So it says, if we consider quantum gravity in certain d+1 dimension, and suppose we have some boundary of these systems, and then this quantum gravity can be described as a certain quantum many-body systems living on the same manifold as the boundary of quantum gravity. And this is so far working assumption, but nowadays we have a very nice famous example from string theory, which is called ADS-shifted correspondence or gauge gravity duality. And in this example, what we are thinking about is quantum gravity in asymptotically anti-digital space. This is a negatively curved, constantly curved space-time at the asymptotic infinity. So under this boundary condition, we can consider quantum gravity, and it can be described as a certain gapless system, which is conformal field theory. And of course, we have to specify further the property of CFT, conformal field theory, but since it's not relevant to today's talk, let me skip the detail, but it's also important problem. And also we know that explicit example. But how it's related to the tensor network? Actually, it's very much related to the tensor network. Since today we focus on a version of ADS-CFT, it's related to the conformal field theory, a gapless system. So let's focus on the tensor network describing the ground set wave function for the gapless system. So this is a particular example which is called MERA. I suppose you are very familiar with it. And actually, this tensor network shares the same entanglement structure as the quantum gravity in ADS. So first, let me briefly explain how it is related. And as you probably know, in the tensor network, if we compute, for example, entanglement entropy associated with subsystem A with size LA, and we just tracing over its complement, and then we can estimate the total number of the entanglement for this digit density matrix. And it's roughly estimated as the number of unitary operators and its number of bonds which cutting this line. This line is determined by when we decompose our density matrix to the two pieces, subsystem A and its complement. And the number of this isometry, so sorry, not isometry, but unitary transformation, is roughly estimated as the depth of this layer is scaled with log LA. So as you know, entanglement entropy for such a vacuum in CFT proportional to the log of the subsystem size, if we consider 1+1D CFT. But actually, we can view this cutting line as a kind of length of the geodesics, since it takes a minimum value and also counting the number. It's roughly speaking the length of this line. Actually, we have the same structure when we compute entanglement entropy by using gravity. So this is so-called Ryu-Takayama formula or its generalization. But today, let me just focus on the simplest example. So for simplicity, let's consider ground state in the CFT. And maybe we are thinking about 1+1D. And then we have dual geometry, which is just empty ADS. There's nothing. It sounds natural because the low energy state should be related. Okay, and then we can consider entanglement entropy associated with subsystem A in vacuum state, ground state in CFT. So we keep our subsystem A here and tracing over this part. This corresponds to the boundary of ADS, but it's also related to the manifold in the CFT. And then programmatic calculation of the entanglement entropy says that this entropy associated with subsystem A corresponds to the so-called area of the minimal surfaces. I'm writing here. But if we consider 1+1D CFT and dual 2+1D gravity, this minimal surfaces is nothing but a geodesics, which anchors on the boundary of subsystem. And it's well known that if this time slice of ADS is just a hyperbolic space, so the geodesics is just a semicircle on the Poincare disk. And you can easily calculate this geodesic length, and indeed it proportions the log of the total system size in the boundary. Okay, and so in this way, actually we have the very similar structure of the entanglement for tensor networks and also quantum gravity in ADS. And in the case of the gravity, we have some interesting relation between structure of the entanglement, since I'm computing the entanglement entropy, but it's also related to the structure of the geometry, since we compute it from the some geometrical object determined by the geometry or metric. Okay, although it's not very much relevant to today's talk, let me just show you more correspondence between tensor networks or idea of the quantum information and quantum gravity in ADS. I'm not going to tell you the detail of this correspondence, but I just want to say there are many correspondence, and sometimes tensor networks can also teach us something important property of quantum gravity. As an example, we can consider certain quantum error correcting code, which consists of the some hyperbolic tiling of the perfect tensor. It is sometimes called happy code, found by these authors. And interestingly, this tensor network model also have the same structure of the entanglement, and also give us the insight of the how we can construct the bulk operator in the gravity by using boundary CFT operators. There were some puzzle for gravity side, but this tensor network model or quantum error correcting code give us explicit resolution for this puzzle. So in this way, tensor network is more than the tool. It also tells us very important aspect of the quantum gravity. So far, I have briefly explained some interesting connection between tensor networks and quantum gravity in ADS, and also its connection to the quantum information theoretic quantities like entanglement entropy. But today, I'd like to discuss especially this part. So in the gravity perspective, we can expect or we can naturally think about some more general geometrical object, which should be well defined, at least in the framework of gravity. Then it's natural to ask which kind of boundary CFT quantities can compute such a geometrical object. Since area is related to the entanglement entropy, which is a very fundamental quantum information theoretic quantities, it would be nice to see the correspondence between more general geometrical objects and certain quantum information theoretic quantities. And in some cases, it might be something new, not known in literature. And we have some successful example, for example, like this. And today, I'd like to tell you one particular example, which is pseudo entropy. By the way, as I have already explained, since we have nice connection between tensor network and gravity in ADS, although today I start from gravity and go to the quantum information theoretic quantities, it's also natural to start from tensor network argument and finding some natural object defined within the tensor network and finding the new quantum information theoretic quantities. So this is very interesting, another future direction. Although today I don't have any concrete discussion. It would be nice if we could discuss this direction. Okay, so let me back to our work. And here is a heuristic. But from here, I move to our work, but I could start from the formal definition of the pseudo entropy. But here, let me do a heuristic derivation, since I expect it will be also useful to do the similar things from the tensor network. So let me do in this way. So for this purpose, I have to explain one dictionary in the ADS, CFT correspondence holography, but I hope it will be natural for you. Since ADS CFT correspondence says the quantum gravity in ADS and certain CFT is the same, it means that the spectrum of the Hamiltonian should be the same. So if we accept this concept, partition function should be the same since we have the same spectrum. And since partition function can be regarded as a kind of generating function of the correlation functions, we can also have the variant of this dictionaries. It means that we can calculate correlation function from the gravity side. And for the CFT, quantum minimal system side, we can interpret certain partial function or correlation function as the inner product between two non-normalized states. It sounds a bit artificial, but in principle, we can always do this. And on the other hand, in the gravity side, we can imagine at the semi-classical limit of the gravity, we have particular geometry. And here I'm writing the time direction here, but technically speaking, this is a Euclidean time related to the preparing the state in the CFT side. And roughly speaking, the future, we have future and past, and future part corresponds to the final state, phi, bar phi, and past part corresponds to the initial part, psi. So roughly speaking, this inner product is described in the gravity side, particular geometry, and quantum field theory living on it. And this geometry is given by one dimensionally higher gravity. And I would like to use this dictionary to calculate the entanglement entropy or a more generalization. And if we compute entanglement entropy holographically by using this dictionary, since we are interested in the density matrix, we have to consider a very particular types of the geometry. It means that since we have physical state, it means that our matrix has the same state in the Bra and Ket. So if we apply the previous dictionary in this example, future state and past state should be the same. So in other words, we have some reflection symmetry along this time slice. This is so-called, and okay, but on the other hand, if we compute entanglement entropy, the dual geometry has a very particular symmetry. However, from the gravity perspective, as I have already explained, we can naturally think about more general geometry. But in this case, there are no longer reflection symmetry, since the future and past states can be the different. But at least from the gravity perspective, we would like to understand the structure of the metric from the boundary perspective. But unfortunately, entanglement entropy cannot probe this geometry, since these types of geometry, since we have no reflection symmetry, nothing to do with the entanglement entropy. But there are very much simple replacement compared with the previous entanglement entropy, because we have two different states in the future and the past. So it means that although we started from the density matrix when we compute the entanglement entropy, we can just replacing the one of two states to the another one. Then we have the transition, so-called transition matrix. And these types of transition matrix could describe this type of geometry. And of course, here I implicitly assume we have non-vanishing overlap between this initial and final state, so that we have meaningful calculation. So let's go back to the question. So so even if we started from the more general geometry, entanglement entropy cannot probe the this type of more general geometry. However, we can, at least in the gravity side, naturally define the, for example, minimal surfaces. For example, we can naturally define geodesics in this space-time. But fat kind of quantity we can fat kind of quantity in the boundary can capture such a general geometrical object. That is a question I want to answer. And but from this intuitive argument, it's almost obvious. All we need to do is just replacing the density matrix to the previous transition matrix and compute the von Neumann entropy. So in this way, we come up with the idea of the pseudo entropy. And since this is quite a simple replacement, we can give a proof of the this type of formula, namely computing the pseudo entropy can indeed computing these types of more general minimal area surfaces in the gravity side by assuming radiation-shifting correspondence. But since today I'd like to discuss more applications of the condition of matter physics, let me skip the detail. Okay, so anyway, in this way, from the gravity argument, we can naturally imagine some generalization, at least in the gravity side, and it with pseudo entropy. So from here, let's forget about gravity and introduce pseudo entropy. So this is some formal definition of the pseudo entropy. So it means that previously we computed entanglement entropy, which is the von Neumann entropy of the reduced density matrix. But here we replace all density matrix to the transition matrix. So roughly speaking, pseudo entropy is given by in this way. Here, this TA corresponds to the reduced transition matrix, which is obtained from the tracing over subsystem of the transition matrix. And as a reminder, I should write again. It's given by in this form. Okay, but to be precise, this definition is a bit naive. And since now we have transition matrix, which is no longer Hermitian matrix in general, it means that it's not obvious to have some diagonalized form of this transition matrix. So to be precise, we define this quantity from its eigenvalue, or in other words, we can use Jordan normal form to define it. So more precisely speaking, we started from the linear version of this entropy by using this part, this expression, and taking n to the 1 limit, assuming the analytic continuation, we obtain the formally this expression. Okay, this is the definition. And I have several comments on the basic property of pseudo entropy. And as I have already explained, now we are thinking about transition matrix and its von Neumann entropy. Since transition matrix is no longer physical state, pseudo entropy can take complex values in general, since the eigenvalue of the general matrix can be complex. Nevertheless, as we will see later soon, in some nice class of states, actually pseudo entropy gives us the real value. And in particular, in many examples, we have real positive value. And also, if we think about entanglement entropy in non-Hermitian systems, for example, entanglement entropy for the eigenstate in the non-Hermitian systems, we can naturally interpret it as a pseudo entropy, because since our Hamiltonian is now not Hermitian, left and right eigenstate is not the same in general. So in this way, our density matrix naturally interpreted as the transition matrix in this example. And furthermore, we have some information theoretic interpretation of this pseudo entropy. In particular, its real part. We can interpret it as the number of distillable EPR pairs during the post-selection process. Since I don't have enough time today, I don't explain the detail, but I have to comment that we can interpret in this way, but it's not proven in generic way. So we use particular set of example and argue we can interpret in this way. So it would be nice we can give some more general proof. Okay, but this property, it would be nice, and maybe transition matrix or its reduced density matrix can provide some non-Hermitian generalization that not the Hamiltonian, but the entanglement Hamiltonian. And also, if we consider this pseudo entropy associated with two vacuum states for some different quantum field theories, it typically follows the area law as like the standard entanglement entropy in the quantum field theories. And in particular, we have confirmed this statement in the free fields. Okay, in the rest of my talk, I'd like to discuss the application of pseudo entropy to the quantum math physics. First, I will discuss pseudo entropy can detect whether or not given two states associated with the pseudo entropy in the same quantum phase or not. And later, I will also discuss pseudo entropy can be used as a characterization of the entanglement spectrum itself, as like the spectrum form factor and Hamiltonian. Okay. Any questions so far? Okay, good. So let me go to the applications. Okay, so for this, let me define the following quantity. So we take the real part of the pseudo entropy, like this, and we subtract averaged entanglement entropy. So here I have imagined in my mind some transition matrix given by two states, and taking the reduced density matrix for this. And this averaged entanglement entropy means that we have two density matrix, and from this, we can define entanglement entropy for the first state and second state. So average entanglement entropy means average entanglement entropy associated with the two states belong to the original pseudo entropy. And if we study it in the quantum field theory, in many cases, we can see the real part of the pseudo entropy is smaller than the average entanglement entropy. But if we consider more general state like gap system, it's not necessary to be the case, at least as far as we observe. And the main statement of this part is, if we consider this delta S12, it can be positive when two states, this one and two state, belongs to the different quantum phase. This is our claim and confirmed in several examples. And one advantage would be the following. So since if we use entanglement entropy as the order parameter, we need to vary the parameters. But in this case, we need just a 2 parameter points to see whether this delta S12 is positive or not. So it may be computational advantage. I'm not sure whether it's to what extent useful, but maybe it's an advantage. Okay, so from here, let's go to the concrete example. So here I'm writing the Hamiltonian for the XY spin chain. So we have two particular parameters, gamma and lambda. For the specific gamma and lambda, we have various types of the models. For example, if we take gamma equal 1, we have transverse Ising model. And here I'm writing the phase diagram, and just let dashed line correspond to the transverse Ising model. And we have several critical lines corresponding to the particular parameters. And this green line corresponds to the critical XY model with C equal 1/2 central charge. And we also have another central critical line for the XX model. And in this case, we have C equal 1 critical central charge. So for example, if we consider the two-state vacuum state in Hamiltonian, living on the this part and this part, these two states belong to the different quantum phase since it's across the critical line. But if we consider, say, two states living on the same quantum phase, please notice that this Ising line is not related to the critical line itself. This is just a parameter region for the Ising model. So, for example, in these 2 points, these two states belong to the same quantum phase. So the question is that this delta S12 can detect such a difference. Okay. And for the actual computation, this is just a technical comment, but we can generalize so-called correlator method. It is useful and famous method to calculate entanglement entropy. And we can generalize it to the pseudo entropy. And for this, we can compute entanglement entropy for the infinitely large total systems. That is the advantage to use this method. Okay, so let me show you several examples. First, let us see the two-state vacuum state in the previous Hamiltonian living on the same phase. So for example, if we have one of two ground states living on this point, and suppose another state living on the same point, but then we gradually change the parameter for one of two states in this zigzag line, we can see the behavior of the pseudo entropy or average entanglement entropy. And since in this case, we have two states always in the same phase, nothing special should not be happen. But indeed, as you can see from this figure, in this parameter region, pseudo entropy is always smaller than the average entanglement entropy. I pick up particular parameter region, but anyway, these two parameters living on the same phase. So in this example, delta S12 is always negative. Okay, but how is the case where two states can be living on the different phase? So here I'm focusing on the line for the transverse Ising model. And let's consider one vacuum state, a ground state, living on the one phase and another state living on the another different phase. So we have two states living on the paramagnetic phase and ferromagnetic phase. And in this case, what happens? If still we have two states on the same phase, pseudo entropy is less than or equal to the average entanglement entropy. However, once our two states goes to the living on the two different phases, then interestingly, pseudo entropy can be larger than the average entanglement entropy. So in this way, the positive sign of this delta S12 suggests the given two states associated with the pseudo entropy are living on the different quantum phase.
A question, please.
Please.
What is the horizontal axis of that graph?
Horizontal. This is the. Sorry. Which graph? This one?
Yes.
Sorry. This is lambda 2. So this is the parameter for the. Sorry, maybe this is quite small. This is the parameter for the this Hamiltonian, and
so
we have two. Oh, sorry.
So that characterizes the distance from the critical point. Is that right? So I'm a bit confused.
Exactly,
yeah, I'm a bit confused because Hamiltonian itself is Hermitian, but you have chosen two states from the above the criticality and below the criticality. So what is the parameterization in that graph and in that state?
Okay, so I should say we have two parameters in the Hamiltonian, gamma and lambda, and whether or not these two are suppose lambda is larger than gamma, in this case we have this phase, and if gamma is smaller, we have another phase, and this green line corresponds to the critical line. So above this line, and below the line, we have different living on the different phase.
So the point 1, the state 1 and the state 2 are living in the different points in that phase diagram. Is that correct?
Yeah, exactly.
Okay.
So for example, one state is living on here, and we move another state in this direction. And if these two states living on the same phase, pseudo entropy is less than or equal to the average entanglement entropy. But once our state goes to this another phase, then we have interesting behavior. So pseudo entropy can be greater than the average value.
Okay, thank you.
Sorry, maybe, yeah, sorry for that. Actually, this horizontal axis is quite small. This is the parameter for the second state. And yeah. The particular, this is just a particular example, but for example. Okay, so any other question for so far? Actually, I will show you another example for the similar phenomena. Okay, so let me show you. We can do the same things for another critical line. So we have critical XX model here, and again we have we fix one state to here, and second state move to this direction, or maybe I'm being opposite. Sorry. So I fix first state here. Okay. I was right. Yeah, first state here, and we move second state to this direction. And in this case, actually, before crossing this critical line, our two states belong to the different phase, and the pseudo entropy is greater than average value. But once we cross this line, pseudo entropy go back to the go back to be smaller than average value. Okay, so in this way we can confirm at least in these two critical lines, we can discuss from the sign flipping of the delta S12 or positivity of the delta S12, we can argue whether or not two states belong to the same phase or not. So at least in this example, so delta S12 can be used for detecting the two states belong to the same phase or not.
Excuse me,
Please.
I have a question about the crossing point between the average interconnect. Is it
Okay.
different from two critical lines?
Right. So I have to say, if it is positive, it is different phase, but sometimes it's still negative. Even if so, yeah. There are kind of subtlety of the some lattice effect, but I would say in positive case we can. I am confident to say these two things are the different phase, at least in this example. So it's not necessarily sufficient condition.
Nice.
I would say.
Okay, thank you.
Yeah, but I would say if it's positive, it at least in this example definitely belongs to the different phase. And I expect this is because if these two states are in far distance, structure of the entanglement is quite different. So that's the way why positivity can appear here. Okay, so in this way, at least if our delta S12 is positive, we can say these two states living on a different quantum phase. So this gives us some sufficient condition, at least in our example. And next, since I don't have, okay, I have time, so I will explain the pseudo entropy as a characterization of entanglement spectrum. Okay, so there is a quantity so-called spectrum form factor, which is nice characteristics of the energy spectrum in the chaotic systems. And here I'm writing a specific example for the SYK model. I have some Majorana fermion and have some random coupling following the Gaussian distribution. And in this case, a spectrum form factor is roughly speaking proportional to the amplitude of the analytic some complex temperature partition function. And here, imaginary part corresponds to the time direction. And if we plot it, we have particular behavior of the in the chaotic systems. For example, first we have some slope region at the early time, and it stops and growing. This part sometimes called ramp, and again it stops, and we have some plateau region. And this line corresponds to a kind of averaging over the coupling. But if we pick up a particular coupling, we have some erratic oscillation here. But the average behavior can be understood as this curve. And in particular, we have two characteristics: time, which is so-called Saurus time, or deep time, and Heisenberg time, or plateau time. And this time is, at least in this example, scaled with the size of the total sites. For example, Saurus time scaled with the square root of this total system n, size n. And Heisenberg time is given by the total system size n. Okay, and we can actually reproduce these types of spectrum form factor from the gravity argument, but semi-classical gravity computation only give us the average value. So from the gravity, we can calculate this average value, but we need something more to reproduce erratic noise here. So from this, we can now recently people expect gravity, semi-classical simple gravity can be related to the rather ensemble average over the certain systems. Of course, full theory should reproduce this erratic noise, however. But here, let me ask the question: can we do the similar things for modular Hamiltonian or entanglement Hamiltonian, it is given by the log of the reduced density matrix. It is also important quantity to characterize the subsystems. And for the simplest example, let's consider the reduced density matrix for the thermal state. So here I have canonical Gibbs state and tracing of a subsystem, and the remaining density matrix is given by rho A, and then ask the question whether this modular Hamiltonian for this state, which kind of property we can see from the and we will use pseudo entropy as our probe. And since I don't have enough time, I will skip the detail, but for this, we can use so-called sum of field double state. Since transition matrix is only defined for the pure state, we have to purify the previous thermal density matrix to tracing over subsystems. So this, we have two duplicated systems, and basically we trace over one of them entirely, and we keep subsystem A. So this right system corresponds to what we are actually thinking about, and this left system corresponds to the duplicated system in order to define transition matrix. And let's suppose total system size for these right systems and the left system is capital L, and this subsystem A corresponds to the small l. And assume temperature, inverse temperature is beta. And first, let's consider L to the infinity limit, I mean large volume limit, since it's the most simplest example. And in this case, it is known that if we consider 2D CFT, 1 plus 1D CFT, the entanglement Hamiltonian is universal. And indeed, we can obtain the analytic result for the pseudo entropy associated with this setup, and it gives us this simple analytic form. Okay, and it's rather natural to have a universal answer because our entanglement Hamiltonian is also universal. But first of all, I can see some characteristics time. Maybe we can say it as a subsystem Saurus and Heisenberg time, because its scale is not the total system, but the subsystem, size of the system A. So here I'm plotting some different subsystem size and temperature, and from this figure we can confirm as the time flow ending the oscillation is scaled with total system, total subsystem L and small l, and also end of the slope can be scaled with the inverse temperature times subsystem L and taking the square root. And also, although I'm showing some particular figure, we can understand this characteristic behavior even from the previous analytic expression. Okay, then so far I have only discussed the very universal result, but let's go to the more non-universal part. So for example, if we consider Ising CFT with finite system size, then the density matrix, a reduced density matrix, has a non-universal entanglement spectrum compared with the other CFT. And if we do so, actually we can see the erratic oscillation. And since this Ising CFT is integrable system, we can also see the quantum revival around the after the Heisenberg time, but scaled with total system size. Since I'm taking some log plot, it's difficult to see, but we have some revival here. And we can also compute similar finite size calculation for the gravity side. And in this case, we can still use the previous formula according to the holographic calculation. And it means that gravity again gives us a self-averaging result. So it's consistent with our expectation. And in this way, we can use the pseudo entropy as a characteristic of the spectrum of the entanglement Hamiltonian. Okay, since time is up, let me summarize. I have discussed some tensor network can provide toy models of the quantum gravity. And sometimes quantum gravity tells us the generalization of the quantum information through the quantities such as entanglement entropy. And as an example, we discussed such an example, pseudo entropy defined as the von Neumann entropy associated with reduced transition matrix. And we have seen pseudo entropy can tell us whether two states belong to the same quantum phase or not, and also play a role of entanglement spectrum form factor. And there are a bunch of interesting possible future directions. For example, pseudo entropy itself is not widely understood as much as the entanglement entropy itself. For example, we don't know the interpretation of imaginary path in general. So it's very nice to study further pseudo entropy itself in many quantum many-body systems. It would be nice to better understanding of the pseudo entropy itself. And although I didn't have enough time today, we can apply it to the quantum gravity itself, and we can learn something. And there are several work, including myself and with my student. And also, it's very nice to observe pseudo entropy by experiment, as like the linear entanglement entropy. And also, as I have already mentioned, since quantum gravity features quite similar structure as the tensor network can tell us some such an interesting generalization. Can we tensor network also tell us something new quantum information theoretic quantities? If you are interested in, I'm very happy to discuss this direction. So let me stop here. So thank you for attention.
Thank you for a nice talk. So, please, Okunishi-san, I'm sorry. Is there any question about comment?
Yeah.
Nishino-san, please.
Yeah, I have a question about the transition matrix. I'm working on chiefly two-dimensional statistical models such as classical Ising model on square lattice. And let us think about cylindrical system. It means that the width is L and form the cylinder and the cylindrical direction, say, rounding direction is imaginary time beta. In that case, the partition function is the trace of the nth power. N is the length of the cylinder. Around the how to say circle. Anyway, z partition function equals to nth power of L, the transfer matrix. Okay, so in that case, the power of the transfer matrix is the density matrix, and it is symmetric. Okay, this is the situation, and when the system is uniform. But if the model contains randomness, so for example, the coupling constant J is dependent on on the bond randomly. In that case, the density matrix is not symmetric. It becomes asymmetric. So my question is whether this density matrix can be considered as the transition matrix you have spoken or not.
That's very interesting question. Can I ask? So this is transfer. Maybe we can identify transfer matrix as a transition matrix. Is it possible?
Transfer matrix only can be. Okay. So there is no need that psi and phi correspond to a large area of the two-dimensional classical system, but even a short strip can be identified as a transition matrix.
Short strings.
Yeah. So the transfer matrix is just a short region, narrow region.
Okay. I see. Maybe we could define for this short system, but also we can consider some product of them, and I suppose it's still like some state between two different It is
Okay.
not like this. Yeah, maybe we can. Yeah, maybe in this limited situation, I could imagine we can have some transition matrix and define pseudo entropy, but it's a kind of classical system. So I'm not sure whether how we can interpret it as a quantum. Maybe you have some idea in mind.
Yeah, one-dimensional in two-dimensional classical system can be identified as a 1+1 quantum system.
I see. So I see. So yeah, then it's possible, I think. Yeah.
Okay, thank you. I
Yeah,
just
thank you.
thought upon a comment that because of this asymmetry, we have a difficulty of applying the tensor network scheme for the such a random system. Just a comment. Okay, thank you.
Oh, I see. But yeah, okay.
Okay, Okuni-san, do you have a question?
Yes, I want to ask about the modular Hamiltonian defined for the pseudo entropy. I think for the case of the usual entanglement Hamiltonian, it defines some time evolution on the space-time where the role of time and space direction is swapped. For the case of the pseudo entropy, pseudo entanglement Hamiltonian, does it define any particular time evolution on the space-time, some space-time? Can you give some particular interpretation for the as a time evolution for the entanglement Hamiltonian for the pseudo entropy?
I see. Yeah, thank you for asking this. Actually, at least in the quantum field theory example, we can form. Although what I have explained is this is that Euclidean time direction to prepare the state, but we can taking some analytic continuation to the Lorentzian time, and it at least works well in the certain quantum field theory examples. So in this way, at least we can see this is actually some initial state and final state in the real Lorentzian time direction. So I think it's possible.
Do you have any concrete example of such as space-time for the pseudo entanglement Hamiltonian?
Okay. So actually, sorry, I skipped some detail, but the fact I'm doing in the spectrum of the entanglement Hamiltonian is just something like this. So we have here real time, not the Lorentz, not the Euclidean time. And in this case, we obtain this. But unfortunately, typically, if we consider Lorentzian time in some asymmetric way, it sometimes have some complex value, but the real part still give us very meaningful answer. And we also have some gravity interpretation, for example. So we have some dual geometry which describe some entire behavior of this, for example, spectrum some generalization of the spectrum form factor.
Anyway, this data and T represent this temperature or time in the original space-time.
Yeah, right, exactly.
I see.
This is just one example, but yeah. Thank you for asking.
Okay, next question from Ivan Pavlov, please.
Yes, a question, please.
Yeah, please.
Thank you for your talk. It was very interesting. I have a question regarding the definition of the pseudo Renyi alpha entropy.
Okay. Wait a moment. Okay, here, this one.
Yeah. So normally when you work with the density matrix, you can prove that the Renyi alpha entropy is a decreasing function respect with the, in this case, the n variable. But can you say the same thing when you're working with the transition matrix?
Okay, so that's an important question. And yeah, at least I don't have general proof.
Oh, okay.
But yeah, this is short answer, and in some case, maybe we can check, for example, holographical equations suggest
Oh, okay.
decreasing function or not. But I'm not sure for the general proof. Maybe it's not very defined. Yeah, that's important
Okay,
question.
thanks.
Thank you. Yeah.
Okay, next question from Akiyama-san, please.
Well, yes, can you hear me?
Yeah.
Well, I have a very naive, maybe a naive question. If I remember correctly, you mentioned that pseudo entropy in certain class of system, the pseudo entropy usually takes the real and the non-negative value. Is that also the and you calculated the pseudo entropy in the kind of XY spin chain model?
Yeah.
And in the total parameter region of the your XY model, your spin model always takes the data pseudo entropy always takes the non-negative and the 0. Is that right?
Thank you for asking this. To be precise, we have some exception. Let me explain it if time is allowed. Yeah, for example, if we here I'm writing this dashed circle. In this line, we have some degenerated vacuum in the original systems. Is XI model, and when we across this line, somehow we have kind of imaginary contribution.
Imaginary contribution.
So this is roughly speaking. If we crossing here, the spectrum of the entanglement Hamiltonian, some spectrum changing the sign, and it will give us the imaginary part. So maybe imaginary part may be used for such a situation, but I have no clear answer. But anyway, in some situations which I didn't explain today, we still see some imaginary piece, or yeah, I should say.
Is that possible? We can say something about the how can I say? Can we get some information from the sign of the pseudo entropy itself? Is that or always we have to consider the delta is some kind of the difference between the real part of the pseudo entropy and the average entanglement entropy?
Not necessary. For example, if we consider some non-Hamiltonian system, but with some critical point, there's some work by Sensei Liu and his collaborator. They consider some energy, some state on the non-Hamiltonian systems, and they can see there are some critical line, and the entanglement entropy in this case, I should say it's kind of a pseudo entropy, can detect this phase flange. And in this phase point corresponds to the C equal -2 conformal pseudo. It means that entanglement entropy is always negative. So we can even find we can capture some non-unitary CFT from this pseudo entropy.
I see.
So I would say negative value can be also important for some situation, but I don't have a full picture, or yeah. But yeah, it's very interesting.
Okay.
Yeah.
I see. Thank you very much.
Thank you.
Okay.